Okay, this is to help you work your way through the chemical pathways poster. These are the slides that we'll be looking at, so you can come back and work out what we're up to. So we're going to work our way along here to start with, from alkanes to carboxylic acids. So you can see as you go across, alkanes, chloroalkanes, alcohols, aldehydes and carboxylic acids, as you move your way across, they're becoming more and more oxidized. Ultimately, the carbon is becoming more oxidized. The most oxidized carbon would be is if you had it with carbon dioxide. So carbon dioxide should really be off the screen over here. So all of these are becoming more oxidized as you move across. So we're going to start with alkanes. The first thing with all of these steps, you need to know the names of the reaction, the reactants that you need, and any bits of help that you might need to for the activation energy. So heat or light or a catalyst to lower the activation energy. Alright, so we're doing the first row to start with. So we're going to start with alkanes. And as I was saying, moving from left to right, the carbon compounds becoming more oxidized. So a way of knowing if something's more oxidized, the ratio of oxygen to hydrogen, you get more oxygen when it's oxidized. So obviously to get more oxygen, you can add oxygen or you can remove hydrogen. So losing hydrogen means the molecule has also become more oxidized. So from alkanes to carboxylic acids, you're going from a carbon attached to a hydrogen to a carbon that's now got two oxygens. So oxygens are gradually added. And as I was saying, complete oxidation. The carbon is completely oxidized when you've just added oxygen and you don't have the hydrogens anymore. So adding oxygen, removing hydrogens. Okay, so the first ones that we're going to look at, the first reactions, are alkanes to chloroalkanes to alcohols, or chloroalkanes to amines. So these are all substitution reactions. So they're the first ones that we're going to be doing. So substitution means swapping. In the textbook it goes into all of the chemistry of why they swap, which you can read about and understand, but basically you're going to swap a hydrogen for a chlorine in the first step. So you're going to put, instead of having an alkane with carbon attached to hydrogen, you're going to have a chloroalkane. When you're swapping the hydrogen for one chlorine, so the other chlorine and the hydrogen that you've swapped are going to produce the hydrochloric acid as well. So that's the other thing that will be produced. As well as swapping with chlorine, you could swap it with bromine. But basically we're just going to be doing chlorine on our poster. It needs a bit of help, so to lower the activation energy, or to give some energy to break the bonds, to overcome the activation energy, you need a bit of ultraviolet light. So remember, you need chlorine to swap this hydrogen so that you get a chlorine molecule, and the other chlorine and the hydrogen will get together to make hydrochloric acid, which is not written, the other product is not written on these things. An example is methane. So you've got the 4 hydrogens. You're going to swap one of those with a chlorine to get chloromethane, and the other hydrogen makes the hydrochloric acid. So you're writing whatever aids that you need above the arrows. So the thing is, if we leave this chloromethane sitting in the reaction is happening and you've got lots of chlorine molecules around, those chlorine molecules will still be around when you've made this product. So more reaction can happen. This chlorine can now react with the chloromethane again and swap another hydrogen for a chlorine to make dichloromethane. So the longer that you leave it sit there, the more the dichloromethane can be swapped again to make trichloromethane. The longer you leave it sit there, the more hydrogens will be swapped for chlorines. We're interested for the whole pathway in having the chlorine being swapped on the end of a hydrocarbon molecule, okay, which will make more sense later. Okay, so we've now swapped our hydrogen for our chlorine, so we're going to swap the chlorine for an OH to make an alcohol. So the easiest way is to use a hydroxide. Hydroxide ions are negatively charged. The negative charge will push the electrons further away, repel these electrons. The chlorine is also electronegative, so the electrons are being attracted to the chlorine anyway. So as that approaches, the electrons move and go over to the chlorine totally. And then the electron here will form the bond with that electron that's no longer bonded. So it will make a methanol molecule. This is showing just a hydroxide floating around all by itself, but clearly you'd have something else with it, so sodium hydroxide or potassium hydroxide. So the chlorine that has been detached would make sodium chloride or potassium chloride. So remember that when you're swapping, you're making some other molecule as well. So we're swapping our chlorine for an OH to make an alcohol. You can also swap it, a water molecule, have an OH. This is not as strong, won't work as well, as easily as having the negative charge on a hydroxide ion. So you need a bit of help if you're using water. So you need a catalyst, but you can get the same reaction. So either one of those will make an alcohol. Okay, so we've done our substitution across here. You can also substitute the chlorine for nitrogen and hydrogen to make an amine. Okay, so this is an ammonia molecule. Nitrogen forms 3 bonds. At the moment, the nitrogen is forming 3 bonds with the hydrogen, but you can swap it with the chlorine. So it will form 2 of the bonds with the hydrogen, and the other hydrogen will form a bond with the chlorine to make hydrochloric acid. So that's our other small molecule, hydrochloric acid. Okay, this is if the chlorine is on the second carbon and you've swapped it to make propan 2-amine. So haloalkanes containing, we've been doing it with chlorine, but if they've got fluorine, bromine or iodine, then you can also swap these with the strong base, hydroxide, to make an alcohol, or ammonia to make an amine. So it will also work with the other halogens. Okay, if there's a fluorine, a bromine or an iodine here, you can swap them as well. You have to use chlorine though, because I think chlorine is a stronger reactant. You can't use fluorine or, well, I don't know. Okay, so we've done substitution. So the next bit along here, these are all redox reactions. So it's kind of weird that they accept redox here, but not here. They prefer you to call it substitution. As I've said, the whole thing, redox reactions, all of these molecules are being oxidized. They're all redox reactions, but anyway, they'll accept redox for here. So we're turning an alcohol into a carboxylic acid. In the past, we used to just go straight from an alcohol to a carboxylic acid, but now we're doing this intermediate step. So we're turning the alcohol into the aldehyde and then turning it into the carboxylic acid. So you can see what's happening. We're adding oxygens, remember, to oxidize it. So you've added this oxygen here, becoming more oxidized. As you're going from here to here, it's actually lost a hydrogen, which is not so obvious here. This carbon has got 2 hydrogens attached to it. But when you get over to here, you've got the double bond has lost a hydrogen. So it's being more oxidized because it's lost a hydrogen. Okay, so in order to go from an alcohol to an aldehyde, you need an oxidizing agent. To go from alcohol to an aldehyde, you need your OH on the end of the molecule because the carboxylic acid is going to be on the end. So to get the carboxylic acid on the end, you need an aldehyde on the end, so you need your alcohol on the end. So an alcohol on the end is a primary alcohol. And you're going to react that with a strong oxidizing agent. So you need to remember this formula, Cr2O7, 2- dichromate, di-2-chromate. It could have something attached to it, metal, so potassium dichromate. And it needs a catalyst, a bit of help to get the reaction started, so hydrogen ions. So it needs to be in an acidic solution. So you can write it needs to be an acidic solution, acidified dichromate, something like that, or just say that hydrogen ions need to be present. You can also use the oxidizing agent for manganate. So this one I remember Cr2O7 2-. This one's MnO4 1-. So we need, in order to have a carboxylic acid on the end, we need a primary alcohol. So this is a primary alcohol. Primary alcohols are when the OH group, hydroxyl group, it's attached to a carbon which is only attached to one other carbon. This is a secondary alcohol. The OH group is attached to a carbon that's attached to 2 other carbons. And this is a tertiary alcohol. The carbon it's attached to is attached to 3 other carbons. So to make a carboxylic acid, we need a primary alcohol. We need our hydroxyl group on the end. So if we've got a primary alcohol, it's on the end, then it will be oxidized with this oxidizing agent and turned into the aldehyde. So it's lost a hydrogen, become more oxidized, and then over here, more oxygen's being added, so it becomes even more oxidized. So you can see that you're using exactly the same reactants. So this reaction will keep going to form the carboxylic acid. If you have it at a cooler temperature, then this reaction will be very slow because you won't have enough energy to form this. So you'll be able to isolate the aldehyde. But if you leave it for long enough or you heat it, then eventually this will get turned into a carboxylic acid. Okay, so we've done our whole row. So you need to practice alkanes, chloroalkanes, alcohols, aldehydes, carboxylic acids. So we're going to do the next bit here, alcohols to carboxylic acids to make esters. We've done this before. No, we're not doing that. Go back. I missed this one. So we've done primary alcohols. So secondary alcohols, if you have your hydroxyl group in the middle, then it will swap. Instead of making an aldehyde, a double bond with a hydrogen, you've made your carbonyl group, but it's got 2 carbons on either side. So you've made a ketone. Okay, so I missed that bit. So same need oxidizing agent and the acid. but your secondary alcohol. And the tertiary alcohol up the top, tertiary alcohol where you've got the carbon is bonded to 3 other carbons, nothing will happen, no reaction. Okay, now we do the esters. So, esters are carboxylic acids and alcohol together. We did this in year 11. It's a condensation reaction because it also makes water as well as the ester. So condensation reactions, there's quite a few of them where they make a small molecule. Water's the classic sort of one. So we've got our carboxylic acid, COO, and we're going to react the alcohol here so that you end up with the Q in the middle. So this was the carboxylic acid, and then we're going to add the alcohol. To do this reaction, you need sulfuric acid, you might remember from last year, as the catalyst. Okay, back to this one. So that's our ester, alcohols and carboxylic acids, making a Q. You can also do amines and carboxylic acids to make an amide. So instead of a Q, you've got that this was a carboxylic acid. So instead of a COO, you've got a CON for the amine. So if you just react it with ammonia, nothing else, then ammonia will go right on the end here. Right on the end here, I should say. So you have the CO from the carboxylic acid and the ammonia added onto the end. That's a primary amide bond. If you're, as we're coming along here, we had our carbon, swapped it, put a amine group on the end. If you react this with your carboxylic acid, then this is a carbon. So that's a secondary amide where you've got your carbon. So example, carboxylic acid, ammonia, just ammonia. So you're putting ammonia right on the end. This looks unusual, doesn't it, for a carboxylic acid? I get used to seeing them like this with the carbonyl group sticking straight up. But so we're swapping to make water, and then that is going to be bonded directly to the carbon. So you've got your amide bond, CONH. CONH. Okay, you kind of get, so rather than a Q, you've got a CONH. Remind yourself, so an amide bond. So that's a primary amide. A secondary amide is when you have your amine group attached to a carbon. So you get like not just the NH right on the end, primary. It's got a carbon and a carbon. So the nitrogen is attached to 2 carbons. Okay, secondary amide. Okay, so that's on the top of your poster. So just like just like the esters down the bottom, but it's amides on the top. Hydrolysis, hydrolysis. What is the name for the reaction which is the opposite of a condensation? So it's hydrolysis. Hydro means water, lysis means breaking. So with making an ester, you produced water. If you want to break up an ester, you use water. And then you get your carboxylic acid and your alcohol back again. So if you use sulfuric acid to make an ester, then you would use a base, potassium hydroxide, to break up an ester. Okay, so I don't have that on here. So it's condensation reaction this way, would be hydrolysis the other way, to break up the ester. Okay, so now we're doing alkenes over here. Okay, so these reactions with an alkene. Alkenes are where a molecule is reacted with an unsaturated hydrocarbon, alkene, and it breaks the double bond and the molecule is added. That's why they're called addition. You're just adding them. So you add something to one carbon and something to the other carbon on either side of the double bond. And you only make one product. So you add the alkene and whatever it is that you're reacting together and you make one thing. So our example, our first example, we're adding the same chemical, so something like bromine or hydrogen. The reason I picked bromine is the classic test for an alkene is to react it with brown bromine. How handy is that? Br, Br. So bromine is brown. If you've got a double bond and you react it with bromine, then it will go clear. So it's a test to see if you have a double bond. If you don't have a double bond, then nothing will happen and you've still got your brown bromine. So what happens is this is an electron from this carbon and an electron from that carbon being shared. Instead of being shared with each other, the electron from here and the electron from here, that will break, and this electron and that electron will form a new bond. And this electron and the other electron from here will form a new bond too. So these break so that you end up forming a new bond. So you must add something to one carbon and something to the other carbon. Okay, so we've done it with bromine, which are the two things that are the same. If you did it with hydrogen, you need to remember that you need a catalyst, metal catalyst, to help you. If we do it with hydrochloric acid, so if you add hydrogen, you turn an alkene into an alkane. If you add hydrochloric acid, a hydrogen has to go onto one carbon and the chlorine has to go onto the other carbon. Remember to break your bond. People always seem to, like, they've got a double bond here and they still end up putting a double bond there. And don't get tricked. You know, you're not going to add these things to the same carbon. You have to add them to the different carbons. If this was around the other way, this at the moment, the chlorine has been added. You notice that this goes up. This has got 4 carbons. They've just been drawn like this. So it's been added to the second carbon. If we swap those, turn those over, it could be added to the first carbon. So you can add the same molecule to these and end up with 2 different chloroalkanes, depending on which way around this molecule was facing. So which of these isomers would form a carboxylic acid? So you remember, as you're going along from alkane to chloroalkane, etc., etc., you need to have your chlorine on the end, so you get your OH on the end, so you get your aldehyde on the end, so you get your carboxylic acid on the end. So this one, 1-chlorobutane, has the chlorine on the end, so it could form a carboxylic acid. This couldn't. If I go back here, so this is fairly easy to remember, but water is a weak reactant, needs a bit of help. You need to remember you can't just write catalyst like we can here. We can't just cheat for this one. You actually have to remember that it's phosphoric acid catalyst and you need a high temperature, 300 degrees. So you have to remember for water all of this, which is kind of a classic question. So we can make an alcohol by breaking up an alkene, or we can make an alcohol by substituting the hydroxide for chlorine. So 2 ways to make an alcohol. Okay. So water molecules, OH, is going to go onto one of the carbons, and the other H, is going to go on the other carbon. So your water molecule here has broken, and it makes an alcohol. Okay, we need to do the last one here, addition polymerization. You might remember in Year 11 I got everyone to stand up and hold hands to form a double bond. So a person here with their 2 hands and another person here with their 2 hands or forming a double bond. Same here. And then I've got these people here to let go of one of their hands and form a bond between them, which is what this bond here and this bond here is. So if you have a whole lot of people and both hands are being held by somebody else, they can still hold hands, but they can let go and make another bond. So the electron, instead of being shared with this carbon, this electron now here is being shared with this carbon to make a bond. So what you need to know about these are monomers. We've kind of vaguely talked about this. Mono mean one, like on a bike, you're doing on one tire. Poly means many. So if you've got a whole lot of monomers and you join them together, you make a polymer. These are ethane monomers. If you put them together, you make polyethane, polythene. Instead of writing, however many, because this will go on and on and on, because you'll just keep adding monomers. It goes on and on and on. Polythene is glad wrap, so you can make molecules, as long as you like. To represent that it's a section of something that's really long, you just draw an open bond here. So there's nothing bonded to it. It's just implying, because it's a bond with nothing on the end of it, that it's continuing. And another way of doing it is you just take one monomer, have it broken, and have these ends open to show that it's going on and on and on. And then you say N. We've got a certain number of our monomers. So this is a way of representing a section of a polymer. And then you would get a mark for the open brackets. Okay.